Okay, this is our introduction to Unit 1718. We're doing a quick little review here of exponential and logarithmic functions. So we're going to start with exponential functions because I think those are the kinds of functions that you are sort of most familiar with or you've had the most experience working with. You can see up here the format of an exponential function. Y equals a to the x, and a, of course, is what we call the base of this function, and it's just some number in most cases. So we could have something like y equals 2 to the x. And you know that the graphs of these exponential functions, they start sort of way over here like this, and they're going to go kind of up like that. So we've got a horizontal asymptote at y equals 0, and it just continues without bound up to positive infinity as x goes to positive infinity. This, of course, is if our base is positive. So if a is greater than, sorry, not positive, but greater than 1. What happens if our base is less than 1? So we have something like y equals 1/2 to the x. What does our exponential function look like then? Less than 1, yeah, and greater than 0. Good point. Okay, so it's still a positive base, but it is sort of fractional. Okay, like a half. What is our graph going to look like then? Yeah, same thing, but from the other side, sort of a mirror image. It's going to come down like this, like that. So we still have a horizontal asymptote. Now, what is the domain of an exponential function? Let's write this down here. Domain. Luca. Yeah, all possible real values. Okay, because our graphs start at negative infinity, x of negative infinity, go all the way to x of positive infinity. Okay. Logarithmic functions. What do we mean by a logarithmic function? Well, logarithmic functions are the inverse of exponential functions. Okay. So if we've got some function y equals a to the x, we can rewrite that by taking the inverse, interchanging x and y, and rearranging as x equals log to the base a of y. So if we've got a function like, in the earlier example, we looked at y equals 2 to the x as our exponential function. Okay. Our corresponding logarithmic function would be y equals log to the base 2 of x. Okay. So if these guys are inverses of each other, what is the graph of log to the base 2 of x going to look like? How do you take the inverse of a function graphically? What do you think, Luca? Yeah, we imagine we've got this line y equals x, and then we sort of reflect our function y equals 2x in that line. So our logarithmic function is going to have a graph that looks something like this. Like that. Okay? It's all well and good. Yeah. Log y. Okay. The big thing that we want to realize at this point is what is the domain of a logarithmic function? This was the whole point of me drawing these graphs. Omar. Yeah. X is an element of real numbers. X must be greater than 0. Okay? So this point is going to be kind of critical for us. We have to remember that we can never have an x value in our logarithmic function that is, or an argument in our logarithmic function that is going to be equal to or less than 0. Okay? So as I promised, stars next to the important things. Okay. All right. You guys also took a look at the laws of logarithms. So you learned 3 laws for simplifying or working with logarithms. You learned the product law, which basically said if you're taking the log of something that's a product of 2 things, you can break it into a sum of 2 separate logarithms. There's the quotient law. If you're doing the logarithm of 2 things that are divided by each other, you can break that up into 2 logarithms that are subtracted from each other. You looked at the power law. Log of something that is, something to some power. You can bring this exponent out front and get p log a to the x. Okay? So we're going to use these laws in a number of cases when we are taking derivatives, because sometimes we want to simplify the function that we're taking the derivative of. Rewrite it in a form that makes it easier to do the derivative. We're also going to be using these things when we are solving logarithmic equations, which we're going to have to do, because what's the big thing I keep asking you to do in this course? Take a derivative, set it equal to 0, solve. Okay, so we're going to have to spend some time solving logarithmic equations. These laws come in handy when we do that. So I put together a little example here of applying all these things together. Let's say I want to take this expression here, 3 log to the base 2 of x plus log to the base 2 of x minus 3. And I've said simplify it. What if I just, basically by simplify, I want to write this as a single logarithm. Okay. First thing I'm going to do is I'm going to check to make sure that my bases are all the same. Okay, I've got log to the base 2 and log to the base 2. That's good. If the bases are different, you really can't do anything with it. What am I going to do next if I'm simplifying this guy? What do you think, Adam?
Put the 3 to the, so it's x log to the base 2x cubed.
Yeah, I'm going to use that power law in reverse to get that. What am I going to do after that? What else can I do with these guys? Luca? To get what? Yeah. Yeah. So I can basically have inside the argument of my log function here, x cubed times x minus 3. And then if I wanted to, I could, well, that's already in factored form, so that's probably better. I could expand and simplify if I needed to, but I would probably just leave it like that because the thing inside is factored. Okay. I've got, all right. Here is the other thing that is going to be pretty important here. Using the change of base formula, okay? So, what is the change of base formula? What it tells you is that if you've got log to some base of something, base a of x, you can change this into any base that you want by taking the log of the argument x and dividing it by the log of the other base, as long as you're using the same base in these 2 logarithms. So when I write something like this, log x, log a, if I don't show a base there, like I don't say this is base 2 or base 5, what base do you assume that this is? There, base 10. So this, you could think of this as log to the base 10 over x, log to the base 10 of a. And you guys use this, I think in advanced functions, you used it mainly if you had something like log to the base 2 of 7, and you wanted to evaluate this on your calculator. Because your calculator does log to the base 10, you could take this and say, okay, I'm going to rewrite this as log to the base 10 of 7 divided by log to the base 10 of 2. And then both of these things you could punch into your calculator, divide them, and work out what it is. Okay? Why is this going to be important in our course? In our course, we are going to be working with what we call base E. Now, what do you know about E? Luca, what do you know? It is a constant. E is equal to, well, is approximately equal to 2.7182.818, but it goes on and on and on and on and on. Okay, it's one of these irrational numbers that is never going to terminate, never going to repeat. Okay. What else do you know about E? Anything? Have you used it before? Adam's shaking his head. Honestly, I don't know. Why would we? Basically, okay. Omar, what were you going to say at the back?
It was something that I was gonna ask you about, and I had no idea what it was until yesterday. I researched online and found out that it was a constant.
Okay. Okay, it is pretty confusing. Yep. All right. So tomorrow's lesson, 1718A, is all about what is E and why we are going to be using it. Okay? And we're going to be using it because it makes doing the calculus an awful lot easier. Okay? For now, we'll just say that E is a constant. It's a base that we're going to be using all the time. And we use it so often that we have a special notation if we're doing logarithms to the base of E. So a log to the base E of x is what we call the natural logarithm. Okay? And it's given the notation ln. Okay? And it's pronounced ln. So log to the base E of x is actually ln of x, is what we're going to say. And that just means take the logarithm to this special base. And it's called, so ln stands for logarithm natural. I don't know, maybe it was French originally and they always put the words backwards, or maybe we put the words backwards or something like that. So base E is often called the natural base. Ln, or log to the base E, is called the natural logarithm. Okay? So often when we get something that is a logarithm to some other base, we are going to want to change it into something that is in base E, and that's where this change of base formula is going to come in. Okay? Now, just recall here a couple of properties of logarithms. Okay, so let's say, oh, and exponential functions here. So let's say I've got something like this, log to the base 10 of 10 to the 2. And I wanted to evaluate this thing. What would this evaluate to? Luca, how did you get 2?
Power laws, but go in front, then in the base law to get log 10 over log 10, 1, and 1.
Okay. So he says, okay, use the product rule. I'm going to bring this exponent out front, and then I've got log to the base 10 of 10. What I would kind of remember here is that anytime you're taking the logarithm to some base of, and the argument of what you're taking the logarithm of is the same as your base. I mean, if you're doing log to the base 10 of 10, the answer is always, this is always just going to be 1 here. And so you're just going to be left with that 2 here. Okay? Why does this work? Because remember, what does a logarithm mean? It means what exponent am I going to have on this base to get this number? So if my base is 10 and I want to get 10, my exponent is going to have to be 1. So the answer there of that log to the base 10 of 10 is just 1. So you can kind of imagine when you're looking at something like log to the base 10 of 10, that log and that thing there just sort of cancel each other out. Okay? So similarly, let's look at one like this, ln of e to the 7. So remember, ln is just log to the base e of e to the 7. So what is my answer going to be here? Adam? Just 7, yeah. You can imagine this log to the base e and that base e canceling out, and you're left with just 7. Okay? Gone, gone, and you just have the 7. Now, conversely, what if I have something like e to the ln of 2? Okay? So this is, in my exponent, I've got the ln of 2. In my base, I've got e. Okay? I think the way to remember this is that putting something to some exponent and doing some logarithm, they're like opposite operations. We've talked about these since grade 9, right? Opposite of addition is subtraction. Opposite of multiplication is division. Opposite of taking the square root is squaring, okay? And when you're solving an equation, you can do these opposite operations to get things to kind of cancel out. So imagine that raising something to some power, or putting something as the exponent to some base, and then doing the logarithm to the same base are opposite operations, and they're just going to cancel out, okay? So if I do e to the log to the base e of 2, those two things are just going to cancel out, and I'm going to be left with 2. Just like over here, log to the base e and e to some exponent sort of canceled out. Okay. So keeping that in mind, if I've got 2 to the exponent log to the base 2 of 7, how can I think about this? Avery?
The 2 and the log 2 would cancel each other out.
Yeah. Yeah. And the answer is just going to be 7. Now, if a real math teacher came in here and saw me canceling out stuff like that, they would probably take away my math license. But I think this is just a good way of remembering it, okay? All right. Wait, was there something else I wanted to do on this page? I don't think so. Okay. So, here we come. This is the last thing we want to do here. We want to be able to solve equations that involve exponential functions and logarithmic functions. Okay? So we'll start pretty simple here. Let's say I've got this exponential function, e to the x equals 7. I want to solve this thing for x. The process that we're going to use is we're going to work on both sides of the equation at the same time. We are going to do opposite operations. Okay? So if I see e to the x, what is the opposite operation to doing e to the x? Omar.
Log the base. We have to log it.
We have to log it. And what base are we going to use? Not base 10.
Oh,
What base do we see?
7.
7. No, that 7's not our base. What is our base here? On the left side of the equation.
Oh, okay, then the e.
Yeah, so we want to do log to the base e of both sides. So I'm going to write that as ln e to the x equals ln 7. Opposite operations do the same thing to both sides. Well, what do we know about ln of e to the x, or log to the base e of e to the x? What is that going to simplify to? Yeah, it's just going to be x, okay? Because those things sort of cancel out. So we're left with x equals ln 7. And we're done. Ln 7 is just a number. You can punch that into your calculator. The other base that your calculator will work with is base e. So there's a button on your calculator that just says ln. So you can punch in ln 7 and it'll give you an answer. Okay? But most of the time we don't want the decimal answer. We want it as just ln 7. All right, the next simple one here. Let's say we've got ln of x equals 9. Okay, we want to solve for x again. Again, we want to do opposite operations. We want to work on both sides of the equation doing the same thing. So if we see taking the ln of something, what is the opposite to taking the ln of something? What's the opposite of a logarithmic function? It's an exponential function. So we want to somehow work this into an exponential function. So what we're going to do is we're going to take the left side here and we're going to put it as the exponent in an exponential function with the same base. So I'm going to use base e, so I'm going to have e to the ln x because I want my base of my exponential and my logarithm there to match. If I do that on the left side, I've got to do the same thing on the right side. So I'm taking both sides of my equation, putting it as the exponent and a power with base e. What's going to happen on the left-hand side of my equation here? I've got e to the ln x. What's going to happen here, Mahar? I'm just going to be left with x. That e and that log to the base e, or that ln, cancel out. Okay, and then I'm done. Okay, because e to the 9 is just 2.71 blah, 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 blah to the power of 9. You can punch that into your calculator too. It's got an e to the x button that you can evaluate. Luca.
Can you just rewrite them since you have something harder?
Yep. I often make a mistake when I try that. Well, when they get more complicated, I often make a mistake when I try to rewrite them. So I often just think to myself, this is what I'm doing, and it helps me remember. Rewriting it is more mathematically correct. I find this easier to remember. So it's up to you. All right. Let's look at something like this guy here. 4 to the x minus 2 equals 8. We want to solve this guy for x. What do you think we should do? Adam.
I know this isn't logarithms, but can you just do 2, then square root or parentheses x minus 2, and then sub that in using like regular exponent rules, and then for 8, 2 cubed, and then just do the
Do you want to get the same basis and then
Yeah.
can't cross out the bases?
Yeah.
Yeah. You can do that. That'll work with this one. Okay. What if it didn't work with this one? Omar, what would you do?
We log both sides by base 10, then you do the product rule.
Okay. So hold on.
Sorry, the exponent rule, sorry, and then you use the quotient rule because, x minus 2. Yeah, that stuff.
You're way ahead of me. So we want to take the log of both sides. I like that. You said you wanted to use base 10. Okay. So I get log of 4 to the x minus 2 equals log 8. What did you want to do next, Omar?
I want to use that power rule.
Okay, so you're going to bring the x minus 2 out front times log 4 equals log 8. Okay. Where did you want to go from here?
First, I believe we should. I believe we should expand that. Like x minus 2 that's up. I think we can write that as x log 4 minus 2 log 4.
We could. I don't think we want to, though. I think that's making things more confusing on the left-hand side. We want to work our way down to where we just have x all by itself on the left side. So it'd be nice if we could take something from the left side, shift it over to the right side. What's an obvious candidate for something to move here, Avery?
Divide both sides by log.
Yeah, let's divide out by that log of 4. So over here I get log 8 divided by log 4. Okay? And now I don't even need these brackets over here, so I'm going to erase them. I got x minus 2 equals log 8 over log 4. How do I solve this thing for x here, Luca? Just add 2 to both sides. Okay? Log 8 over log 4 plus 2. And now you've got something that you can put into your calculator here. Log 8 divided by log 4 gives you 1.5. You add the 2 and you get 3.5. Okay? It doesn't matter what base you use when you're taking the logarithms. You could have used base e here, done ln of both sides, which is what I'm going to get you to do in Unit 1718, is just get in the habit of using ln every time. Because when you get down to this stage, it's like the two bases sort of cancel each other out. All right. A trickier one over here. Log to the base 8 of 2 minus x plus log to the base 8 of 4 minus x equals 1. We want to solve for x. What are we going to do? You did ones like this last year in advanced functions. I know because I took this one right out of the advanced functions learning guide. How are we going to start this guy? What do we think? Dare, any thoughts?
Would you expand out the brackets and then back?
What do you mean by expand out the brackets? Yeah. I mean, that's the thing about these brackets, right? Is you can't, these things are the argument of this log function. So you can't really expand them out unless you were applying one of those product rule, quotient rule, or power rules, okay? So if we've got 2 minus x, that's got to stay as 2 minus x inside that log. But we can use one of those laws to rewrite what we have on the left-hand side here. How can we do that? There. Yeah, we can use our product rule, and we can rewrite this as log to the base 8 of, going to be big square brackets here, 2 minus x, 4 minus x equals 1. Okay. What would you do from here? Go ahead, Maya. Okay, so you're going to expand out this thing inside our big square brackets, multiplying these binomials, so we get 8 minus 2x minus 4x plus x squared. Is that right? Okay, and then I'm just going to collect those like terms. X minus 6x plus x squared. Okay. Where are we going to go from here? At some point, we got to deal with this logarithm. So how can we deal with that log to the base 8 thing? Ideally, we'd like to get rid of it. What do you think, Levon? Yeah. So make it into an exponential equation, or as I was saying, think of it as raising both sides, using 8 as your base, and putting both sides up in the exponent. Log to the base 8 of 8 minus 6x plus x squared equals 8 to the 1. Okay. Now, on that left-hand side, the base 8 exponent thing cancels with the log to the base 8 thing, and we're left with just 8 minus 6x plus x squared equals 8. Now, how would you solve this thing? We've gotten rid of all of the logarithm stuff. What do you think here, Avery?
Would you just solve for x? You would put 8 after the other side and then
Yep, you would. So we're going to basically subtract 8 from both sides, which gets us 0. And then we have over here x squared minus 6x. Avery says we should factor, so I'm going to factor out my x here. X minus 6 equals 0. What are our solutions here? Luca? 0 and 6. Are these both valid solutions to our equation? My hair knows what I'm talking about here. Go for it. Well, you're right that we cannot ever be taking the log of something that is 0 or negative. But let's go back to our original question here. I mean, what he's saying is we need to check the domain here. In our original, we weren't just taking the logarithm of x. We were taking the logarithm of 2 minus x and taking the logarithm of 4 minus x. So we want to imagine subbing in our two solutions here for x. So if I imagine subbing in 0 here and 0 here, okay, I'm taking the log of 2 minus 0, or the log of 2. I can do that. I'm taking the log of 4 minus 0, or the log of 4. I can do that. That is good. What if instead I sub my other solution in here, and instead of 0, I put 6 in here? Well, then I'm taking the log to the base 8 of negative 4 and log to the base 8 of negative 2. Can't take the log of a negative number, so this solution is no good. Okay? We can just say that this is not in the domain of the function. Okay? And this is something you're going to have to get in the habit of doing, is when you get a solution, like let's say the question is asking you to solve for the critical points, get your critical points or your critical numbers, make sure they're in the domain of your function. Okay? Finally, the last thing I want you to get in the habit of doing. Let's say they give you something like 7 over ln 4 minus log to the base 4 of x equals 0. And they want you to solve. The weird thing about this one is we have logarithms with two different bases. We've got a ln, so a log to the base e, and we've got a log to the base 4. We should only ever have one base in any question. So we want to take this and we want to get our bases to be the same. This is where the change of base formula comes in. Okay? So let's take this log to the base 4 and write it as something that is log to the base e. So we'll just do that over here on the side, log to the base 4 of x. What does the change of base formula tell us that this should be? Well, we just have to do ln over ln here, basically log to the base e of both our original argument x and our base 4. So log to the base 4 of x is actually ln x over ln 4. Let's put that in here. How does this help us now? Move this up. Does it help us at all? I don't know. Luca, what would you do from here? Suddenly I have a common denominator, so I can combine these two terms together. What would I do from here if I wanted to solve for x? Keep going, Luca. Yeah, cross multiply by the ln 4. It's just a number. Okay, so I cross multiply, I get this. Then I'm just going to bring the ln x over to the other side. Ln x equals 7. How do we solve this thing here? Here. Yep. So x is going to equal e to the 7. Okay. So get in the habit of using that change of base formula, okay, to get your bases to kind of agree with each other. And we are done. So tomorrow we are going to talk about why E is so important in calculus. Now, there is the first box of the learning guide, box A, goes through one justification for why E is important. I'm going to do something different in the lesson, which I think is a better justification for why we use E in calculus. I would take a look at both of them and decide for yourself who you think is right.